Hello, this is Professor Parker, and welcome to All This Math. Today, we're going to talk about factoring. Now, factoring is a little complex for some people because, well, for one thing, there are several different types of factoring, right, that could be used depending upon what your expression looks like. If your expression is a trinomial like this one, 1, 2, 3, three terms, so that makes this a trinomial, it could be one type of factoring. If it was a binomial and it only had two terms, it could be another type of factoring. If the lead or the degree or the largest exponent in the expression was a 2, there's one type of factoring. Or if the largest exponent was a 3, it could be another type of factoring. So with factoring, you just have to have a lot of experience with knowing when and how to use which method. All right? So that's why it can be challenging for some people. But what I'm going to do is I'm going to break down for you one method of factoring a quadratic. It's called a quadratic because the biggest exponent is a 2, and trinomial. So a quadratic trinomial. All right? So here we have 6r squared minus 17r plus 12. Now also I want to talk a little bit about, real quick, about what factoring actually is. Factoring is just taking an expression and breaking it down into 2 separate parts, or 3 separate parts, or 4 separate parts, right? So that makes it more manageable. You know what I'm saying? Like, it's kind of like, basically, like if you're about to eat some pancakes and you don't want to eat the whole pancake, just pick it up with your hand and eat the whole pancake. You kind of like slice the pancake into smaller pieces, right? Each piece that you slice the pancake into is a factor of the larger pancake. So that's basically what we're going to do here with this quadratic trinomial. All right? Now, the first thing you want to do with factoring is you always want to check to see if there's a greatest common factor. Greatest common factor meaning, is there a coefficient that divides evenly into all 3 of these coefficients, 6, negative 17, and positive 12, besides the number 1. The number 1 doesn't count because if we factor out a 1, that doesn't change any of these terms. So there is no greatest common factor, essentially, of these coefficients, 6, negative 17, and 12. Also, when you check the variables, there's no greatest common factor either. We have a r, and this does not have a r. So we skip the greatest common factor method of factoring. But you always should check to see if there's a greatest common factor, though. Because if you don't, you might end up with a larger expression or a more complex expression than you actually need to. And it would have been a little more simpler to work with if you'd have just took the greatest common factor out. So, all right, so this is a quadratic trinomial. So what we're going to do today is a method called the swing method. Or at least I like to call it the swing method. All right? A lot of teachers may not show this method in their classes because they may be more of an advocate of the trial and error method. All right? And that's something that you do when your lead coefficient is not a 1. So if your lead coefficient is a 1, it's a little more straightforward. But in this case, this is a 6. It's not a 1. So if your lead coefficient is a 6, then you have to do a more involved process. And it's basically just an algorithm that follows about 5 to 6 steps that you can do every time if this expression is factorable. Because you also have to remember that every expression is not factorable. It could be prime, like a prime number. Like the number 3, you can't factor 3 because it only has 2 factors, 3 and 1. The number 5, you can't really factor 5 because it only has 2 factors, 5 and 1. Those are prime numbers. They're not like 16 or 18 or 20 or numbers like 4, you know, that have multiple factors, which are considered composite. All right, so look, this is what we're going to do. The first step, and it's basically an algorithm. It was like I was telling my son yesterday when we were going over some of these problems. If you could play video games and recognize the patterns in video games, then you could do any type of mathematics. Because mathematics is often called the science of patterns. And if you catch the pattern and you catch the flow of it, then you can do any problem. But it has to be taught to you sometimes. I mean, some people might be able to just discover naturally how to do certain problems, but in some cases, in many cases, it has to be taught to you. So once the algorithm is taught to you, and you just practice a whole bunch of problems and you commit the pattern and the process and the procedure to memory, then you could do any problem. So all right, step one. You look at this and you say, okay, well, what's my first number? 6. My last number is 12. So you're going to multiply the first number by the last number. That's always our first step. So we do 6 times 12. And then we know our multiplication facts, so we say 6 times 12 is equal to 72. All right, bet. That's always your first step. Always. Multiply the first number by the last number. All right? And then I'm going to underline the first number and last number, because then we're going to do some things to the first number and last number. Because my next step is to rewrite this first expression. I'm going to rewrite it in a different way, right? So when I rewrite it, now it's going to look like, because I'm going to drop the 6 and replace the 12. So you want to like commit that to memory. Drop the 6, replace the 12. Drop the first coefficient, replace the last coefficient when I rewrite this expression. Now, notice I didn't say nothing about the middle term, because the middle term is still going to be there, right? So I got r squared minus 17r, because look what I did. I dropped the 6. Now, it's not going forever, right? It's going to come back into the mix later on, right? Later on in this problem, right? But for now, I'm dropping it. So I got r squared minus 17r, and then I'm going to replace the 12. But what am I going to replace it with? When we do math problems, we don't do nothing for nothing, right? So I didn't multiply the 6 by 12 for nothing. I multiplied it for a reason, so that product I could use. So that's what I'm going to do with this 72. I'm going to replace the 12 with this 72. Boom. So this is my new expression. This is the original expression, but temporarily, I'm going to use this expression right here. R squared minus 17r plus 72. Okay? So now, there's another type of factoring which is more simpler than this overall method called reverse FOIL. Reverse FOIL, right? Where, because my lead coefficient is a 1, it's a quadratic trinomial, all I need to do is think of two numbers. I call them the two magical numbers that multiply to make 72 and also add up to negative 17, right? That's what I need. What are those two numbers? So I got to know my multiplication facts, right? So I'm automatically thinking about factors of 72. Let me say like 72 times 1. I know that won't work because 72 plus 1 does not equal this number. What about 36 times 2? I know that won't work because that doesn't add up to this number. But you notice how this times this equals that, this times this equals that. I'm looking for pairs of numbers that multiply together to equal the last number, right? And I got to find the ones that fit into the puzzle that also add up to the middle number, the middle coefficient. So what about, let's see, 18 times 4? 18 plus 4 is not negative 17. What about 9 times 8? 9 times 8 is 72, and 9 plus 8 is, but 9 plus 8 is positive 17. So what can I do? Check this out. Negative 9 times negative 8 also equals positive 72. And negative 9 plus negative 8 does add up, is equal to negative 17. So again, sometimes if you get the right numbers but the wrong sign, all you have to do is switch either one of the signs or both. All right? So now, this is how I factor this part out now. I do two binomials like this. I take the square root of r squared, because that's r and r, because r times r is r squared. And then I take these two numbers right here, and I throw them into the mix. So I got minus 9 and minus 8. Now, in case you're wondering, no, it won't make a difference if you were to put negative 8 here and negative 9 here. It still is this expression in factored form. Now, the next step. Remember that 6 that we dropped from the beginning? We're going to bring that 6 back into the mix. All right? By creating a fraction. Create a fraction, right? Underneath of the constants in here. So the 6 goes under here, and the 6 goes under here. All right? Now, when we create this fraction, we always want to check to see if we can reduce it. Right? So can I reduce 9 over 6? Yes, I can. The common factor is 3. So I'm going to have, this is going to turn into a 2 because 6 divided by 3 is 2. This is going to turn into a 3 because 9 divided by 3 is 3. So we do that right here. So now I really have r minus 3 over 2. Over here, the same thing, except my common factor is a 2 over here. So this is going to turn into a 3. This is going to turn into a 4. Now, why 3? If the common factor is a 2, I do 6 divided by 2. That equals 3. I do 8 divided by 2. That equals 4. So now I have fractions. In my final answer, when I factor this expression, I can't have fractions. So that's why I call this the swing method. Because what I'm going to do is whenever you have a denominator left over, you swing that joint. Swing it right here in front of the variable, and you swing this joint right here in front of this variable. So now when I write my final answer, check this out. This is how it's going to look. I'm going to have 2r minus 9, and then I'm going to have 3r minus 4. And look at the mistake that I just made. I just said 2r minus 9, but that 9 is gone. See, you always got to check your work, right? As you're working through problems, you got to check your steps and make sure you got to be on point. So I wasn't on point just now because you swing the 2 in front of the r to get 2r. You should have a minus sign, but I wrote 9, and that was the original number. This is not a 9 no more. This is a 3 now. So I should have wrote minus 3. Over here, 3r minus 4. Okay, I didn't make the mistake over here. Cool. All right, now, this is factor form. This should be the final answer. But let me check to make sure. By multiplying this out, I'll know that it's correct if I can multiply this out and it equals the original problem. That's how I know it'll be correct. All right, so look, you got 2r times 3r. That's 6r squared. You got 2r times negative 4. That's negative 8r. And then I got negative 3 times 3r. That's negative 9r. All I'm doing is the FOIL method. First times first, outer times outer, inner times inner. L stands for last. Last times last. Negative 3 times negative 4 is positive 12. Now, I look for like terms that I can combine. I can combine this and this. All right, so we got 6r squared minus 17r plus 12. And isn't that what I started out with in the first place? It is. So that's proof that this is correct and this is the factored form. Now, I know this might seem a little tedious. It might seem like it's too much. It might seem like it's a lot of steps. But as you get the hang of it, after as you do more and more problems, it's not going to be it's not going to seem that difficult. Because again, it's an algorithm. It's a set of steps. It's a procedure. Once you commit them to memory, you're just going to do it. You're going to pick up the rhythm. See, with mathematics, a lot of times you just got to pick up the rhythm. But you got to do the work until you get to the point where you catch the rhythm, right? Where you catch the beat of it, basically, right? See, when you catch the rhythm, you're like, okay, boom, I see this problem. Okay, I know I need to use this method. All right, multiply the first number by the last number. Boom, that gives me that. Boom, then rewrite the expression. Drop the 6, replace the 12. Now you got this. Then I look for the two numbers, multiply to make this and add up to the middle number. Boom, throw them in the parentheses right there with the square root of the lead term, r and r right there. Reduce my fractions if I can. All right, any denominators, you got to swing them, Jones. You got to swing them, put them in the front, and then that's my answer. And also, I also highly recommend always checking your work. Always check your work. So that way you don't got to ask nobody if your answer is correct. Just check it yourself. All right, boom. And we checked it, we multiplied this out, right? And that's equal to what we started out with. So therefore, that's confirmation that we did the problem correctly. All right, that's it for today. Thank you for tuning in. Please continue to send your sample problems or the problems that you need help with to the All This Math DM, and your problem might make it to this board. Peace out.